going to be a lightning talk about, I'm actually very happy to be sharing this library Kvcached that I'm quite excited by, based on a couple of papers, the PRISM paper that came out this year, and also the GPU multitasking in the era of LLMs paper, and it's aimed at solving the GPU utilization crisis. So, what is that? Well, it is a CapEx crisis that is $300 billion of hyperscaler investment in GPUs and attached data centers, and yet during inference, that's when we're predicting our tokens, we often have only 20 to 40% utilization of our GPUs, and even at peak demand as low as 70%. So, let's talk about why. Why is there such low GPU utilization rates? Well, models have to accommodate a wide range of peaks and troughs in their traffic demand. Idle time's actually been pretty long. 80 seconds plus is the median for over half of the models on chatbot arena. But then the inference request rate can suddenly jump 3x. This first GPT paper shows that within even a couple of minutes. So models therefore reserve capacity for the max possible memory needs to ensure low latency and fast time to first token in those worst case scenarios. Often, by the way, they'll even just allocate one model per GPU. So, why is this? I think probably many of you will know this, that LLMs are auto-regressive in their prediction patterns of each new token predicted by attending to all previous tokens, and yet a lot of those calculations would be redundant, and so we can hold on to our key value attention states, minimizing recompute, but for very long context inference, potentially requiring memory on our GPUs of many tens of gigabytes. So actually memory is more typically the bottleneck in a lot of GPU inference, not compute. There are great, powerful breakthroughs even in the last 2 years. The LLMs team introduced in 2023 page attention that provides a virtualized memory layer. See, I even said refer to diagram. Virtualized memory layer here that decouples the virtual physical memory assignment, but per model, not between models. So at runtime, models do not share in a GPU their memory, even if one suddenly frees up and the other one is at a peak inference moment. So, what can we do? Well, you might say, why can't we share GPU memory between models? That seems pretty obvious. So we can free up idle models' memory to support peak inference of another model, and for compute, that's actually a native feature. You don't even need to configure it. It's automatically time shared, and that is, been around for a while. But sharing memory elastically was not historically a priority based on the type of work that was being done, mostly batched and predictable memory requirements. But LLM inference has a new type of memory problem, and is looking for a new answer. That answer is this really, I think, very promising library out of Berkeley, UCLA and Rice, a really cool team out of those schools, that is approaching it at an operating system level, doing memory allocation across models, Kvcached specifically, key value cache, memory allocation across models, doing the allocation at the moment of inference need. And so you can see an example here, rather than having one fixed static cache per model, essentially, for example, 3 models requiring, worst case, 3 GPUs, we can have a single GPU handling all of these models and their demand for memory elastically at the demand moment. So that's pretty exciting. You might say, really, groundbreaking, I guess. What's it look like? Well, here's from the paper 2 models. You've got model 1 in green, model 2 in purple. You can see when model 1's requests drop, the green line going down, model 2, its requests increase, it can't pick up and leverage the unused memory from model 1. By default, it can't do this due to its, I'm going to be shared half and half here, due to its static allocation boundary of the GPU memory, and therefore we see the orange line there, significantly underutilized our potential Kvcached memory. You can therefore also see that the throughput is also not at its potential maximum. Look at the dark blue line, and that's the Kvcached library hitting in. It's allowing automatic allocation of memory across models at that moment of peak inference for model 2, and you can see now our KV cache, look at the dark blue line, is maximized. Our GPU utilization rate is, at its possible maximum peak. And that's going to be handled automatically for us by this KV cache library. So how? This breakthrough, how is it possible? GPU sharing requires two things. The first is you're going to have cross-model memory coordination. So this is possible, this dynamic memory allocation is possible because of recent CUDA virtual memory management driver breakthroughs. So now you're able to access and delegate and separate the initialization of physical and virtual memory on your GPU, and therefore at a model initialization, assign virtual memory per model, and then only at the moment of demand peak, and you do need to write a demand-aware scheduling algorithm once it wrote, do you actually assign the physical memory to the given model? Definitely come to questions, sure. This, though, is going to be breaking to a VLLM type service. The KV cache team is actually really cool, enable you to use a single flag because under the hood, they are exposing the same torch type interfaces that PyTorch exposes and remaining accessible to CUDA kernels. And so you are actually not going to need to make any changes to your engine design, nor to your model deployment. So, pretty cool. The second thing you're going to need if you're suddenly switching models quickly is the reactivation time needs to be minimized. The latency problem of switching models would make this untenable unless, as the designers of KV cache came up with, ways to keep activation latency or reactivation latency low. They've solved that with a pre-created pool of engines, so think execution contexts, for our models, and then also parallel model weight loading as opposed to sequential. So, what does it give us? It gives us a very promising way of designing our GPU provisioning, and you've got an example here in the benchmark that they use of 3 Llama models running on a single GPU. You can see with a conventional approach designating a third of GPU memory per model for the KV cache, that the time to first token is pretty unrealistic for a production experience. The latency is too high. However, that's the blue bars. But once you introduce the KV cache library and have that memory allocated at inference time dynamically, we can achieve far more production-ready time to first token results. So, rather than provision multiple GPUs to handle multiple models, we can actually handle them on a single GPU. So, very exciting. If you want to use the library, there's the library link. These are the 2 papers it's based off. It works for the VLLM and for SGLang. Olama is on the roadmap. It works for NVIDIA chips. AMD coming soon. They have great Docker images you can just download and deploy to your remote server of choice very easily. So you can go and rent your expensive GPUs, but slightly less expensive. But I actually think it's really fun to do on your own machine as well, because especially on your own machine, running a background model, we were talking in the groups earlier about what do you do when inference is happening. Well, one thing is it would be nice when inference isn't happening to free up memory on your local machine automatically. This library is well suited for doing that as well. So there's interest maybe in bringing in the creators of the library. So as I say, some of them are based in Berkeley, and I'm meeting with one of them next week. And that would be perhaps quite fun. And if any of you are interested in the sort of new stuff happening in model infrastructure design, particularly in more constrained environments, for example, embodied AI, then I would love to chat more. So there you go. Thank you, everybody. And I want to come and